discuss oxygen content, oxygen delivery, explain how oxygen is carried in the blood and delivered to tissues. What are the relevant equations for oxygen content and delivery? Explain oxyhemoglobin dissociation curve. Discuss how oxygen delivery can be clinically optimized. Discuss 5 causes of hypoxemia, hypoventilation, VQ mismatch, low FiO2, shunting and diffusion, impairment, and calculate expected PaO2 for a given FiO2 or PaO2, and discuss significance of increasing AA gradient.
Which question is that?
2A.
2A.
She deserves 20 minutes.
Yeah. So first things I want to describe.
Go ahead and erase that.
All of that?
Yeah. You guys don't get talking points.
That was so much
You
work
want
to
to write
get
it
up
back
there.
on, you can, but
Okay,
it's not fair, nobody else had talking points.
gotcha.
All
So
right.
oxygen content would be how much oxygen we have in a deciliter of blood. So once we breathe in air and oxygen gets diffused to the alveolar capillary membrane, there's 2 places it can go. One is diffused in blood, and this is roughly 3%. And the second would be to loosely and reversibly bind to hemoglobin. That's 97%. So diffused blood, we look at P8O2. This is more so a measure of how ventilation is occurring in the lung, not so much the oxygen content in the blood. So not so much blood O2 content, more so ventilation. We call this unbound oxygen, and we can calculate it with the solubility coefficient of oxygen. And we multiply that by our PaO2. Then we have our loosely bound oxygen to hemoglobin, right? We have 4 parts for oxygen where it binds to heme, has iron-containing pigment, and it reversibly and loosely binds to oxygen. And we calculate our bound oxygen with, let me give you a little background, 1.34 mLs of oxygen is carried in 1 deciliter of hemoglobin, considering that is 100% saturated. So bound O2 would be 1.34 mLs times whatever your patient's hemoglobin is, times your SaO2. So if we really wanted to know what is the total oxygen content in a patient's blood, we combine these 2 to give us our CaO2, right? Let's go here. But it's not enough to have oxygen content in the blood, we need a delivery system. So we get our CaO2, we multiply it by our cardiac output, heart rate times stroke volume, and we need a conversion factor of 10. Why? Because our cardiac output is liters per minute, and our CaO2 is grams per deciliter. So before I jump into the oxygen dissociation curve, I like to keep looking at this in an arithmetic looking fashion on how to clinically optimize our oxygen delivery. We can increase our hemoglobin, right, through either basically a blood transfusion. We can increase the partial pressure of oxygen with supplemental oxygen, or we can increase our cardiac output, whether it be with inotropes or fluids. So now we go to our oxygen dissociation curve. This tells us the percent saturated of hemoglobin with O2, and this gives us our partial pressure of oxygen. One of the things that we look at is our P50, lines up with 26.5 in a normal curve. And our curve looks like a sigmoidal shape, right? One of the things about the sigmoidal shape that it tells us is that the partial pressure of oxygen, it doesn't matter how much you increase it, it has a limited utility, right? So you can increase your partial pressure, it won't really have much effect on your saturation. Another thing we can look at with P50, let me get my colors, would be a right shift or a left shift. And basically, a right shift tells us there is an increased O2 dissociation meaning that hemoglobin wants to unload that oxygen, and this mostly happens in the tissues. So what are some things that increase this? Increased CO2, increased acidity, or a decreased pH, increased DPG, which is basically a glycolysis of the red blood cell that wants to unload that hemoglobin. You see this a lot in pregnancy. Mom wants to give oxygen to baby and placenta. And increased temperature. So one thing that we notice is that these are all metabolic, right? Anything that increases your metabolic demand. Now we're gonna go look at the left shift. We all know left love, right? So the hemoglobin wants to hold on to that oxygen. So the exact opposite is true. Decreased CO2, decreased acidity, or an increase in pH, decreased DPG, which is seen in banked blood, and decreased temperature. And then another thing you can kind of take a look at just visually at this chart is right here. At 26.5, which is a normal P50, if you look at the right, saturation is much lower, meaning more oxygen was offloaded. Versus if, my bad, I did that with blue. Well, let's say green. And if you look at the left, your saturation, oh, that was my bad, should be a little bit higher. Your saturation should be a little bit higher, meaning less oxygen was offloaded onto your tissues. And this one's mostly seen in the lungs.
Before you erase that.
Oh, you liked it?
Can you explain why you have what you just explained?
What do you mean, in the sense of why it offloads?
Yeah, so what do you mean by you have a higher saturation at a lower PaO2?
Same pH, in the curve. So it means at the same partial pressure of oxygen, it's not a different PaO2, it's the same partial pressure of oxygen, you have less offloading of oxygen.
But why? Can you explain?
Because your hemoglobin wants to hold on in that in that state, it wants to hold on to oxygen. It's not so much bound to or offload oxygen in this type of demand. And there's different reasons why. It could be, they see it a lot in the lungs, obviously, because in the lungs you're there, it wants to collect as much oxygen as possible. But it could be because of decreased CO2, decreased acidity, decreased temperature. Okay. I might come back to this board, but for time purposes, because there's a lot. We're gonna go into the 5 things that we see with hypoxemia. And in the midst of it, I'm gonna explain to you what AA gradients are. So the first mechanism could be a low FiO2. Second mechanism could be hypoventilation. And your other 3 could be a VQ mismatch, it could be a shunt, and it could be a diffusion. These 3 all have an increased AA gradient. So an AA gradient is the difference between the oxygen content in your alveoli versus the oxygen content in your arterial blood. And there is some form of discord when it comes to these 3 on how much oxygen is really diffusing and going into your arterial blood. So the first 2 that we're going to discuss for hypoxemia, which is low oxygen in the blood, are going to be FiO2 and hypoventilation. All of them are sources of hypoxemia, right? So they're all going to have a decreased PaO2. The only one that's going to cause an increase in CO2 would be your hypoventilation, right? We see it all the time when we try to bring our patients back, we lower respirations. You're essentially low minute volume, low tidal volume, low respiration. The rest of them can have normal to decrease. When you're hypoxemic, you tend to want to hyperventilate. AA gradient is normal in the first 2. There is no problem with diffusion of oxygen. And will supplementation help? In basically all of them except the shunt, which makes it different, which we'll go over. So low FiO2 can be anywhere from a hypoxic mixture to being in high altitude. Right, at high altitude we're accustomed, sea level, we're accustomed to a barometric pressure of 760. We have water vapor in our lungs, so we always subtract that 47. And then we'd multiply it by whatever percentage of oxygen it is that we're breathing in. In this case, it'd be air. If you put me up in Mount Everest, and my barometric pressure is now 350. I still have the same water vapor pressure, and I still have the same amount of oxygen. My number is gonna be a lot lower in the second one than it is gonna be. My partial pressure in this one is roughly 150. This one will probably be half, right? We have a smaller number that we're multiplying it by. So what can we do possibly when we're up in high altitudes to fix this? We'd fix that oxygen percentage. We'd give supplemental oxygen, and that's why it helps. When we hypoventilate, we see this a lot in our patients in the, well, hopefully not a lot in our patients in the PACU, but it is something that we can see in the PACU if we give narcotics, right? The CO2 curve is shifted to the right. They have a less response to an increased CO2, so they don't breathe as often. The respiratory center does not respond as often. So can we mask it with supplemental O2? We can. The saturation is gonna look nice, but are we fixing the problem? No. We need to fix the minute volume. Increase those tidal volumes, increase respiration. So now we go into our 3 different increased AA gradients. First one being VQ mismatch. We do have a physiological VQ mismatch of 0.8, right? At the apex of our lungs, we have more ventilation, just because of gravity when you're sitting upright. Versus at the base of the lungs, we have more perfusion. This is actually the most common. It can happen with pneumonia, it can happen with PEs, it can happen in COPD. There is some form of, there's no balance between your ventilation and your perfusion, causing this arterial hypoxemia. In which case, because you still have ventilation and because you still have perfusion in certain parts of the lungs, you will still be able to fix it with supplemental oxygen. Why is the shunt not true to this? Well, because in the shunt, our alveoli is getting oxygen, but it cannot come to the blood, right? So we have all this blood flow going through, but no oxygen to perfuse. So in this case, supplemental oxygen would not help. And a diffusion issue would be something like, this would be something like pulmonary edema, by the way, where your alveoli is completely filled with fluid and it doesn't allow for any diffusion. A diffusion issue can be something like pulmonary fibrosis, where you have your alveoli, you have your capillary, but there's some form of blockage. We can flood this alveoli with O2. It will increase the amount of molecules that can possibly diffuse through. Okay, those are your 5 causes of hypoxemia. I kind of explained to you the AA gradient, and now for the calculation. So, to figure out your alveoli oxygen content, we can go ahead and multiply this FiO2 times what I showed you with the barometric or atmospheric pressure. We subtract it by our water vapor. We multiply this by, or we subtract this by our PCO2, or the content of carbon dioxide in our blood, and we divide this by the respiratory quotient, or your CO2 production over your CO2 consumption. If you wanted to know your PaO2, you get 109 H times 0.4. You could also do what I had showed you with the sea level, 760, subtract your water vapor pressure, and then multiply this by whatever your FiO2 is. I don't think I'm missing